This lesson deals with Supplemental Problem 216. You can find this problem in the ECE302 ebook in the Chapter 2 Supplemental Problems, starting on page 35. What's shown here is a full-wave rectifier using only 2 diodes. In order to do that, you need a center tap transformer. Now, having 2 diodes instead of 4, we'll be able to cut the cost of the diode in half. Unfortunately, a center tap transformer is usually more expensive than a single output transformer. When the diodes are vacuum tubes, cutting the number of diodes in half was significant in terms of cost savings. Now, the cost of the transformer outweighs the savings of the diodes. Let's figure out what Vout is, given that these diodes have a forward drop of VD on. Could you add a capacitor in parallel with our Sibel, and again sketch Vout? I've got an AC signal here on the primary. On the secondary, I've got 2 AC voltage sources, equal in value, same polarity, grounded in between. With respect to ground, this is the negative of this one. You could think of this AC source as if it were a battery that was varying, and likewise this one. And you can use that to figure out which way the current's trying to go in the circuit. If this voltage is positive and greater than a diode drop, say 0.7, then current would want to flow in this direction. I guess that this diode is on. And likewise for the bottom one here, I would guess that current's going to flow in this direction. If this was a resistor here, from the voltage source back to the resistor back to the voltage source. But current can't flow in this direction because that's the barred part of the diode. I guess that this is an open circuit. Let's solve for Vout. The rise in voltage equals the drops around the loop. Vout is equal to minus VD on plus V sub S over 2. V sub S over 2 we're assuming is at least 1 diode drop big. This is bigger than this, so this can be greater than or equal to 0. If this voltage is positive, then the current through it is positive, and therefore our guess about the diode being on is correct. Let's check whether this diode is off or not. The rise in voltage is V sub dB. The drop is minus V sub S over 2 minus Vout back to here. This is my minus Vout. And Vout is equal to this expression, V sub S over 2 minus VD on. V sub S over 2 is greater than or equal to this, so this quantity is positive. Taking the negative of that will then make this negative, and of course this is going to be negative 2. All this is less than 0. For the diode to be off, this voltage needs to be less than a positive VD on. But actually it's negative, so definitely off. Here's V sub S over 2. It's going to go up and it's going to go down, sine wave. Let's say that the maximum value here is V sub M. When this is positive, we're in this section over here. And the output is going to look like the input, but with 1 VD on subtracted off from it. So it's just taking this waveform and pushing it down. That's the same we had as the bridge rectifier, except that we had 2 diode drops. Let's see if that also happens for the next half cycle. The input goes negative. Let's assume that it's negative enough. That's more negative than 1 diode drop. In other words, maybe more negative than 0.7 volts. Think of these secondary voltages as if they were batteries that are varying. This voltage and this voltage are negative, so I'm going to show them as a positive battery in this direction. If this was a resistor, current would want to flow in this direction, so I'm going to guess that diode B is on now, and likewise for this diode, that it's off because current can't go into the barred side. Solve for Vout. Rise in voltage is Vout, the drop is minus VD on, and then we have to follow this notation, not this one, of minus V sub S over 2. Remember, V sub S over 2 is a negative number, greater in magnitude than 0.7, so this is going to become a positive number greater than 0.7. The subtraction is going to be greater than or equal to 0. That means that current's flowing in the load, and that current is going through the diode, and therefore that guess was correct. Let's go check this diode over here. Same thing, we'll go around the loop. So the rise in voltage is V sub dA. I have a drop of V sub S over 2, and then minus Vout. Put the value of Vout in here. A lot of negatives here. This is less than or equal to 0. That's negative. Here I've got minus VD on, say minus 0.7. And now V sub S over 2 is a negative number, but more negative than 0.7. This is say minus 2. You'd have a plus 2 here, minus 0.7. It would be a positive number, so we're going to subtract that. Be negative, and then this is a negative number, so all of that's less than 0. And we just have to be less than a positive VD on for that diode to be off, but we're actually negative. The diode is off, and this diode is on. And the output voltage is going to be the negative of V sub S over 2, the negative of this, minus 1 diode drop. So we're going to flip that over and push it down by 1 diode drop. It's exactly the same as the bridge rectifier, except that we have a 1 here instead of a 2. Let's add a capacitor to our previous circuit so you can figure out what's going to happen now. I got my same input going between V maximum minus V maximum. And then what's going to happen here? Well, when this is positive, this diode's going to conduct. We're going to charge up the capacitor, and then we're going to shut it off, and the input will go back down again and come back up, and in the interim, we'll have an RC decay, just like we had before with the bridge rectifier. And then the next signal, V sub B, comes back up, charges it back up, and then discharges. So we got exactly the same response. It's just that we just have one diode on, one diode off, instead of two diodes on and two diodes off. The formulas we derived where we had two VD on would now just be one VD on. Let's see if we can fix up those formulas from page 60 of the Chapter 2 lecture notes. We had that V maximum was the maximum of the peak voltage on the primary divided by N. That's our step-down factor. But now we're dividing that by 2. And then the maximum value is the RMS value times the square root of 2. For the ripple, we had a 2 here. It's going to put a 1 instead. For V out, we had a 2 here. It's going to put a 1. This is still the same. It's V out over R sub L. This is still the same. I sub D is half of I out. Because half of the load current comes from each diode when it's on, just like the bridge rectifier. Now we're going to solve for the breakover voltage for the diodes. Let's go back and take a look at what's the biggest voltage across the off diode. Let's just pick this one here, assuming we're in that first cycle. Take a look at the peak over here. This node voltage here is going to be equal to minus V sub S over 2, which would be minus V maximum. That would be this term right over here. And then the output is over here. We're going to take the negative of this term and then subtract from it this term, which is V maximum minus VD on. What I get then is minus 2 V maximum plus VD on. V maximum is usually much bigger than VD on, so we can approximate that to just 2 V maximum. Well, that's what we have right here, and that's different than we had for the bridge rectifier. How about the surge current? Let me erase this here. We're going to add a series resistance to our windings. Let's put half of it here and half of it here. Be R sub S over 2. This would be R sub S over 2. The surge occurs when this input here is equal to a maximum. In other words, this point right over here, when you first flip the switch on. That's going to be assuming that the voltage across here is 0. At this node voltage, which is V sub maximum, this is grounded. The voltage here is just going to be, if current flows, is going to be one diode drop. It's going to be V maximum minus one diode drop and then 0, and then dividing by the resistance. Same formula we had for the bridge rectifier, except that we have a 1 here instead of a 2. And this is supplemental problem 216.